Hey everybody, this is an introduction to General Circulation Models, or GCMs, one of the most important tools in climate science. Much of what we know about our future climate is based on these models, so it's important for us to understand how they're made, how they're tested, and how they're used. Models are essential tools in science. They allow us to use data to make predictions about processes we can't directly measure, such as things that happened in the future or things that happened in the past. GCMs are built on well-understood physical principles. They use complex math and computer algorithms to predict how energy and matter interact. GCMs are temporal models, meaning that they predict changes over time. Time intervals can vary from year to year to minute. The smaller the interval, the more precise the prediction. GCMs are also spatial models because they predict conditions on all areas of the planet. Grid size is very important. The smaller the grid cell, the more precise the prediction for a given location. GCMs are also probabilistic, meaning that the predicted outcomes from the model are associated with a % likelihood of being right. This is a measure of how accurate we think the model is. In general, the better the data that go into a model, the more accurate the model will be. This figure illustrates how the grid size of the models produced by the Intergovernmental Panel on Climate Change have decreased in size and therefore increased in precision over the years. These improvements have been made possible by the development of better computer technology. These improvements have been very important because it gives both scientists and policymakers and the public a much clearer understanding of the impacts of climate change and our actions to address it. By the way, there is an assessment report number 5 that came out in 2014, and assessment report 6 is due for release in the year 2020. This figure illustrates that the GCMs are not just two-dimensional overlays of the Earth's surface. There is a depth to them. Assessment report 4, for example, had 30 layers to the atmosphere and 30 layers to the oceans. The more layers, the more precise the predictions. The more layers, the more computing power needed too. Now, just because you build a model doesn't mean it's accurate, even if the data are good. So how do climate scientists test their models? They use a method called hindcasting. Hindcasting is using a model to see how well it predicts the climate of the past. To hindcast, modelers plug in baseline data on the climate from a particular time, including greenhouse gas concentrations from that time, and then run the model to see what happens. They run the model many times and then examine the average results and the variation around that average. Because we know how the climate of the past has behaved, we can compare how well the model output matches the historical measurements. Modelers then rework the design of the model until they get acceptably accurate results. So how are models used to predict the future? Well, instead of hindcasting, they do forecasting. For example, scientists can plug in current conditions for Earth, including current greenhouse gas concentrations and the rate of greenhouse gas accumulation, and then run the model many times to see what is the average forecast or prediction for the future. Scientists can use these models to predict what will happen based on different future scenarios of how quickly greenhouse gas concentrations increase or decrease in the atmosphere. These different scenarios are called representative concentration pathways, or RCPs for short. RCPs are very important in climate modeling, and we'll be studying them a lot in the coming weeks.